Dr. Suri leads the NVM and Neuromorphic Hardware Research Group at IIT Delhi. His research interests include semiconductor non-volatile memory technology and its advanced applications like neuromorphic, AI, security, computing, and sensing. Dr. Suri has been globally recognized as a leading deep tech innovator. He was selected by MIT Technology Reviews as one of the world's top 35 innovators under the age of 35 and top 10 Indian innovators under 35 in the year 2018. Dr. Suri received the prestigious IEEE EDS Early Career Award, Young Scientist Award from the National Academy of Sciences, Young Engineers Award from the from the Institution of Engineers, and Laureate Dubrix from the French Nanosciences Foundation. Dr. Suri has filed several patents, authored 80 plus publications, delivered 60 plus invited talks, and led 10 plus sponsored research projects or consultancies as principal Um, i- investigator. Dr. Suri is the founder of IIT Delhi deep tech startup Siran AI Solutions, which has developed multiple innovative technology products and solutions. He also serves as an advisor to leading AI NBM hardware companies and government bodies. Dr. Suri was a visiting scientist at CNRS France. In past, he has worked at NXP Semiconductors Belgium as a senior scientist and CLIT France. Dr. Suri received his PhD from INP Grenoble, France, and master's and bachelor's from Cornell University, USA. Over to you, Dr. Mansoori. Thank you.
Thank you, Chitara, for the generous introduction. Is my slide visible in full
Yeah,
screen?
yeah.
Okay.
All
Yeah. So also, I would like to thank Professor Alex and Professor Chaube for organizing this, for having me here. It's great to be here and talk about some of the work that we are doing. I'll be talking about the memory-centric computing, or some of the work that we have been doing around trying to extract more functionality out of emerging NVM technology or memory devices for various compute applications or applications just beyond storage. Today's talk's outline would be something like this. I'll go with a brief intro and motivation, and then touch upon some specific case studies from our work, and then try to conclude the session. So the motivation, as also in the excellent talk by the previous speaker, the motivation was quite well laid out, that the volume of information that we are dealing with, we are sort of we are living in a system where we are building digital empires. You talk about any field: IoT, smart cities, social media, healthcare, defense, governments, industry 4.0, everything around us is extremely information and data centric. And also the previous speaker touched upon some of these points. Is we are talking about units of storage which are going into orders of 10 raised to 21, things like zettabytes, or creating information which is of the order of 62,000 billion GB, not 62 GB, not 62,000 GB, but 62,000 billion GB. So the point being that enormous amount of information is being created. So the platform or the the physical media where you keep all this information is again semiconductor storage or non-volatile memory technology. So that is one aspect that we need to be cognizant about. The other thing is that, again, when you have this huge volume of information, you need new ways to process it, to make sense out of it, to get meaningful things out of it. So now that's where the part where you have this realization that software alone or analytics alone cannot do the job when you're talking about things of such humongous scale, whether it is either holding all this data or even processing and extracting key information from this data. That's where you really need to work at the hardware level to make a difference, or you just cannot go with your software based shortcuts or optimization. So when we talk about hardware, there are certain things that we are looking into, the so-called optimized or customized or very specific hardware for these kind of applications. And the traits, some central traits that we are looking for over here are things like low power, it needs to be fast, obviously low silicon real estate or low area, and then again the growing concern of security. These things need to be secure as well. So what do we have in the arsenal to accomplish these things? You start with a very regular and mainstream pieces of hardware such as CPUs. You start going to more specific things like FPGAs, GPUs, and then ultimately ASICs or application specific ICs. So I just chose these pictures to convey a message. GPUs to do some heavy lifting, ASICs very precise use case, but an extreme use case, giving you an extreme performance. And this is more mainstream ferrying around of your computation or data and so on. And then this is again a reconfigurable thing which can run on the road and fly as well. So you can this is what we have so far. Now where interesting things are happening is obviously on this count, on the front of ASICs, and more so when we go beyond CMOS. When we go beyond simple transistors and we start integrating new nano devices, or even things like advanced photonics and so on. So that is the domain where things get interesting, and that is where new memory devices or new NVM devices start playing a central role. So somewhere starting from ASICs or going to the next generation or beyond CMOS or beyond pure CMOS ASICs, or let's say hybrid circuits, or where by the term hybrid I mean traditional transistors, CMOS, as well as new non-CMOS devices for emerging applications. Okay. So the good thing here is that this is not just confined to R&D. This is not just confined to academic research. As we speak, the industry at all different scales, whether it is startups, whether it is the tech giants, or mainstream industry, you will find a lot of evidence where the industry is becoming very active and investing very heavily in dedicated hardware for AI or ML, or dedicated hardware just for performance for very specific tasks. So that is a good sign. That gives you all the good indications to work further in a domain like this. If you're a student, or if you're facing this question, what is a subject that I should pursue for research, then it's very rare that you have topics which are still cutting edge on R&D, and at the same time a lot of industry starts being active in it. Mostly the industry follows once the core R&D is done. So this is one of those good intersections that you come across not very often in the evolution of technology. Okay. So the other thing that I want to draw attention on is also the nature of applications, not just the volume of data. So the nature of applications over here, it comes from a basic motivation, is that there is a quest for building more intelligent machines. All your deep learning, ML, AI, neuromorphic, whatever form you may call it, at the end of the day, the basic quest is to build more perceptive, more responsive, more intelligent machines. And so if you just whether it is autonomous cars, if you take any traditional deep network, you start doing a dissection of those workloads or those use cases, what you would realize is that again the volume of data is huge. And the next thing that you would see is that if you draw down dissipation maps or power or energy dissipation maps, you would realize that there are some very interesting observations that the memory-centric dissipation begins to take the center stage. This, for example, what I'm showing here is the breakdown of a Google Net energy consumption. And you can see that almost about 90% of the dissipation in this case is related to memory blocks or memory elements, and only 10% is pure compute, absolutely pure compute, which just comes from transistors or logic. So all along so many years over the evolution of the semiconductor or the electronics industry, there has been a lot of focus on scaling, or primarily on logic. But that is where time is changing now. That one needs to also take a closer look at memory, and memory in such a way that it's just not only density, but also some other aspects, or not just scaling, and some other aspects as well. Okay, so that's where neuromorphic concepts like neuromorphic computing or brain-inspired computing, they show some signs of hope in certain niche areas. And again, as the previous speaker also touched upon this point, that why these things we feel, or we have some evidence that they are efficient, is because they are massively parallel. They're very scalable. They're extremely low power, and they're immune to variability and noise, which is an important point. As you scale technology, you start to see that the technology begins to misbehave, and that is where you need approaches, fundamentally different computational approaches, where the misbehavior by the technology is acceptable by your computation method, where you don't need perfect devices or perfect operations to be done. Okay, so, and then again, these approaches are secure as well. So now, from an architectural viewpoint, as the previous speaker also mentioned, it's different from the traditional one human computing architecture, and this is where there is no strong boundary between storage and processing blocks. So storage and processing, they sort of now begin to overlap or merge. Your computational blocks are able to store locally, as well as your storage blocks are not just storing, but they're storing more intelligently. So memory is becoming intelligent. So whatever the points that I touched upon, whether it's the volume of data, the nature of the demographics of the application itself, or the underlying basis of some of these new forms of computing, they all are trying to underline that memory is very important for them. That is the point that I'm trying to make in this motivation, that why everything is pointing in the direction of memory. So now another interesting thing is that if you look at the device technology, you will see that memory technology is quite underrated compared to logic. And there is you will see that there is a lot of talk about getting 3D ICs or 3D logic transistors integrated, or many chips being stacked upon each other and getting them functional, getting them packaged in a very sophisticated way, and so on. But the matter of fact is that memory, even today, as we speak, like, we have products which you can literally use. You can buy SSDs off the market which have extremely advanced 3D memories already sitting inside them, which we are taking for granted. So in a way, I think it's not an overstatement to say that, I believe that memory technology has far beaten logic maturity in some ways, or the complexity that we see in logic integration, or some of them. So for instance, what some of the macro scale civil wonders that we see, you can see an equivalent even in the world of memory technology. There you're packing, we take pride in structures which have more than 150 floors over 800 meters, and here you have something in less than 100 microns, you have 128 floors. So this is real technology which people are using. Okay, so again, the point being that everything is pointing in the direction of memory, and memory is not so naive like memory technology even of today. It is quite evolved, it is quite mature to solve some of the requirements that are staring at it, with 3D being one of the evidence. So it makes a perfect case. It makes a perfect case both at the side of requirement and at the side of the availability of technology itself. Okay, so that is why this the notion of going more memory centric, or adopting a more memory centric approach in our design methodology, or how we approach all these problems, makes sense. So what we have been doing in our group at IIT Delhi, and a few years before that, ever since during my PhD days, what I've been doing is We look at emerging memory devices, and there are different flavors of these. We have worked with devices such as conductive bridge RAM, oxide-based memories, phase change memories, MRAM, STT, and also some hybrid variants. Now, the common feature is that most of them are resistive, or they work, or the storage principle, in essence, is realized by some sort of resistance manipulation or a resistive state manipulation mechanism. They are primarily two-terminal devices, and you differentiate between different storage states by being able to program or manipulate the resistance of the device, and then being able to sense it. And as the material changes over here, the underlying physics of the switching action changes. Your phase change memory devices, you're talking about different states, amorphous or crystalline, you're talking about chalcogenides. So that's a more thermoelectric phenomena. If you talk about CBRAM kind of devices, you have materials which are solid electrolytes, sacrificial electrodes. That is more of a redox or electrochemical phenomena. Then you can look into devices oxide-based, or the more popularly known memristors or RRAMs. So where they're working on the vacancy or defect-based mechanisms, filamentary devices, non-filamentary devices, and so on. So this is the technology pool that we have been extensively looking at, or we try to look at while attempting different use cases or different applications. Okay. So now, so in our work, we look at these things. On one side, we have the conventional storage applications, and the work that we do on this branch is related to more performance improvement of the devices, the architectures, or just making better storage platforms. And so that is still the conventional storage application, where all you're expecting from the memory is a very high density storage of ones and zeros, and so on. On the unconventional side, it's where the stuff gets more interesting and more exploratory. I can put these applications in two different buckets. First, I like to club them as the bucket of intelligence, and here we have all computational or intelligence, any application which does some sort of intelligence. So there is neuromorphic, machine learning, in-memory computing, or limb logic in memory computing. And then there are some open applications which we have explored, which are more on the analog or mixed signal circuit side, related to imaging, sensing, non-volatile SRAM, TCAM, storage class memory, getting onboard delay generation using memory devices, non-volatile flip-flops, and also more recently some security applications like physically unclonable functions or random number generators, and so on. So at least in our group, at least we work on 10 distinct applications of NVM, and there are several of them where we have some variants which were demonstrated for the first time, or we were able to come up with entirely new paradigms using memory to implement some of these applications. So now, how we do that? It's a bidirectional approach. In some cases, we start with a fixed device technology or with a fixed material stack, and then we try to extract its electrical properties by characterizing it. Next, we move to model it. It can be physical modeling or just simple empirical modeling. And then once you have the characteristics of the device well defined, you can go towards building circuits out of it, building functional circuits. And here a lot of time is spent on how do you actually choose to interact with these devices, or what I like to call a circuit device interaction. How do you actually interface with these devices? And then once you have figured out how you would program or interface with these devices, one can move to architectures, and then from architectures to applications, and finally performance benchmarking. Now there are cases where one would have an application at hand with very specific constraints, and then try to find the optimum device, and that will be a track in the reverse direction. So we try to follow both of these tracks. And just a nutshell. So we started this work really early way on. Back in 2010, we realized some of the first phase change memory based synapses for spiking neural nets, or let's say spike time dependent plasticity based network implementations. And with that, almost more than a decade ago, what we were able to demonstrate in that work were bio-inspired unsupervised learning applications, spatiotemporal learning applications for vision data as well as auditory data. So at that time we were just focusing on synapses, and then from synapses we moved on to building neurons or neuron circuits, and then once we had both building blocks in place, what we could do is we could move beyond just spiking neural nets or unsupervised spiking neural nets and take some detours to new forms of computing, reservoir nets, echo state nets, LSMs, or even the traditional ML deep learning based approaches. So then somewhere around 2015 to 16, we started investigating the more mainstream DL and AI algorithms, and we tried to see how the new memory can play a role inside it. So we have done some work over here where we have tried to come up with or try to demonstrate some non-volatile inference accelerators, and then more recently, so here for the inference accelerators we have relied more on technologies such as MRAM, and then more recently we have looked into NVM based sensing, where storage can make a difference in sensing circuits as well as security circuits, and then some digital and analog forms of in-memory or near-memory computing. Okay. So, so some specific use cases I'll just take you through depending on how much time we have, and let's talk about the synapses, for instance. Now what are the circuit device challenges, or what are the device related aspects that one really needs to answer, or what is the real question that one is answering here is biological synapses, if you think of them in a very abstract or simplified way for building these networks, it's more of a you can think of it as a programmable non-volatile resistor. Now if you do make that simplification, what you would realize is that although it's a programmable non-volatile resistor, it must behave, its resistance evolution or its conductance evolution, or how its conductance changes in response to a stimuli, must follow some rules or must behave in a certain way. And that's where there was also a question in the previous talk about things like linearity. So things such as your learning rules or your plasticity rules, they would start imposing conditions that how the resistance between two states or between two stimuli is supposed to vary or is not supposed to vary. So so the first questions that one runs into while designing these systems is that obviously what are the number of levels or number of intermediate states that the technology needs to offer for realizing your algorithms or giving a meaningful learning performance and so on. Okay, so that is one question that one has to answer. Now it's not just about the number of states. The immediate next question that you need to answer once you have the number of states or weights between two extreme levels is that whether what is the nature of this transition when you go from a very high conductance to a low conductance, and in the reverse direction, whether you have a symmetric transition going in both directions, or you have an asymmetric transition. Now ideally, or in a software network, you may want a symmetric transition, or you may work with a symmetric transition, but what happens that when you start working with real devices, most of the times you see it's an asymmetric transition going from your set or low resistance state to the reset or high resistance state, and vice versa. So now the next important question is that let's say you have a technology that does give you the adequate number of states, and that does give you some transition behavior. So how do you really actually manifest it? How do you extract it? At the end of the day, you'll be able to extract it only by some sort of electronic stimuli, some electrical pulses or some voltage or current pulses that you induce upon the device, that you apply across the device to ultimately manifest these states. So what happens is that if you're demonstrating these concepts on a single device, you can basically take the liberty to formulate any kind of stimuli and end up extracting the desired characteristics. But the moment you scale it up to even a small network or a big architecture, you see that there are a lot of constraints that come on the surrounding circuitry or the peripheral circuitry around these devices, meaning a few liberties that you can take for granted while programming a single device, they would just kill your entire efficiency promise or your entire gain that you get by using these technologies at an array level or an architecture level. So that's what I mean in this point when I say response to identical stimuli. The simplified, extremely simplified version of spiking nets, that spiking neural nets or SNNs that we do understand and frequently utilize for building such systems. The core element, the spike or the action potential in that case, is assumed to be identical. It's binary. There is a spike or there is no spike, and each spike is identical to the other spike. There is no variation between two spikes or the nature of two spikes. So that sort of identical aspect gives you some sort of, it frees you from the need of having some locally intelligent circuit or some circuit which needs to do additional math. But if you're working with these devices, you will come across in literature that to extract the synaptic characteristics, you have to work with all sort of complicated pulse sequences, and that is where you start going or drifting away from the very identical or simplistic nature of the biological action potential, or at least how we abstract it. So that is one point where one really needs to engineer. One needs to find a fine balance between extracting the required synaptic property from the device and at the same time not ending up with a circuit device interaction which is overly complicated for the entire network, because you can, in a way, you can take a single device and have a neuron circuit which is almost a computer in itself, just sitting next to it, making the synapse behave in a way that you want it to behave. But if you scale it up to a full network, you don't want that many computers sitting. Then there is no purpose of building a system like this. You may as well go back to a GPU and start doing those things. Okay, so there are several tricks. There are several, or one can call them as tricks, or several different methods how we get around these problems. For these resistive memory devices, you can play with their programming conditions. You can manipulate not just the pulse widths, but also the pulse rise and fall times. You can work with the compliance currents, and you can also look for cumulative effects. So cumulative effects are usually the most friendly because that is a device response to identical pulses. You keep accumulating pulses. So phase change materials, which were also discussed in the previous talk, are really good at showing those kind of cumulative effects. But then, so we started this work way long ago, and we saw that inside phase change devices, if you follow a certain transition from, let's say, from amorphous to crystalline, you get one kind of behavior, and from crystalline to amorphous, you get completely different kind of behavior. So then you move to a different set of tricks. So that is like changing or engineering the material itself. So one of the things that we did is, we engineered additional material stack layers inside the PCM devices, GST based devices, and by adding additional interface layers, it gave us a better control over how we are changing the resistance. So this is more of a material centric approach. And next, you can see that, for instance, this is a response to identical stimuli, and depending on the pulse width, the conductance change curves are different. So for instance, this curve is for one specific pulse width, this curve is for another specific pulse width. But this is the point to note here, is that this is a cumulative change. You don't need to re-engineer your stimuli pulse, or you don't need to change the nature of your pulse. So this aligns well with your action potential, modifying the weight kind of concept. And but however, the limitation that you do see is that you can only realize this behavior while crystallizing the technology. If you are working in a reverse direction, that is, if you are trying to amorphize, you will notice that in order to gradually keep increasing the resistance of the device, you do need to re-engineer your pulse. So, then we move to the next layer of tricks. To overcome those problems, we build some solutions which can be realized at the circuit level. So to solve this specific issue with PCM devices, we came up with the 2 PCM synapse, where you have a pair of devices which are known as the LTP devices, and then another device which is known as the LTD device, or long-term potentiation, long-term depression, and so on. And then basically what you do is you exploit the crystallization dynamics in both devices, but the overall integration of one device, the LTD device, the way how it is connected in terms of circuit to the output neuron, is that it has a reverse effect, or it has a subtractive effect on the total current that is accumulated here. So even though you're crystallizing the LTD devices, you're exploiting a property which is a cumulative property, responding responding similar to the biological action potentials and synapses, but the effect is synaptic depression, or decreasing the synaptic conductance. So this is one of the many tricks to get around problems like this. So next, is a more interesting and architectural, or say, let's say, a trick which manifests at the level of learning rules themselves. So this work had quite profound implications in the entire domain. And Stdp, or spike timing dependent plasticity, basically tells you that how you're supposed to locally modify the conductance of a synaptic device if you're building it using your neurons and your CMOS neurons and RRAM synapses, based on the correlation between the firing instances of the pre and the post neuron. So what this rule normally tells you, this biologically observed rule tells you that if the pre neuron spikes before the post, then the conductance is supposed to change in a certain way, and if the post fires before the pre, the conductance is supposed to change in a different way. And in cases where so what you see on y-axis, on y-axis here is the delta conductance change, and what you see on the x-axis is the temporal correlation between the pre and the post neuron firing. So this is the region of LTP, and what you see in these dots and these curves is the as observed biological Stdp. So you can see that the biological Stdp tells you that if the time gap between the pre and the post spike is very less, that is where the maximum conductance change has to occur. If that time gap is way too much, then the effective change in the conductance is not that high, and the same goes for the LTD side. So this is what has been observed in biology, but the question is, do we need to do the exact same thing? Do we need to be that biomimetic for let's say artificial systems? It turns out that even if you simplify these rules, you can still get a fairly good performance from artificial bio-inspired systems. So you don't need to exactly mimic. So we came up with the simplified Stdp rule. So this is the illustration of the simplified Stdp rule, and you can see right away the first simplification is that we are fixing the quantum of conductance change. We are not making it a very complex conductance change behavior. So that relaxes some constraints on your device and your circuit. So and that is the system is still able to learn, because that simplification is compensated at a different level in some sort of different parameters, either at the neuronal level or at the synaptic level, and so on. Okay. So the next simplification or the next concept which we exploited was to come up with probabilistic learning rules, or to see if the deterministic simplified, if we can push further the deterministic simplified STDP rules to stochastic or probabilistic STDP. So here what I'm trying to say is that if on one hand you have a deterministic weight change where you have several levels, and the probability of weight change of each level is 1, meaning whenever you want that weight to change to a certain state, it will change deterministically. On the other hand, you have a case where you just have 2 states, you just have binary states, but the probability that the synapse will go into one of these states is less than 1, meaning it's a probabilistic process. So we were able to show that you can achieve equivalent learning performance or inference performance between these 2 systems. So now that is a huge relief for real hardware, because the first point is that you have ended up simplifying the requirement on the number of states from multiple states. Now you are looking at just 2 or binary states. Most of the devices that we do see around are binary state devices, and comparatively there are fewer devices which have MLC or multiple states. So that is the first advantage. The next advantage is that we are talking about probability here, right? So meaning a phenomena which is indeterministic or which does not happen successfully every time, meaning you try to switch the device, each time it does not switch. So in the normal memory use case, that would be seen as a problem, that would be seen as an issue, that would be seen as a device failure, switching failure, or a behavior which is not required. But in this case, it will manifest as a probability. So the modified learning rule on the y-axis, what was conductance change now, is now the switching probability of going from the LTP state to the LTD state. So if you are able to build networks with this kind of probabilistic rule, what you have ended up essentially with is a very scaling friendly, technology node scaling friendly system, because as you're scaling the technology, right, there is a lot of variation that starts creeping in. It becomes more difficult to control these nano devices as you're scaling them, making them smaller and smaller. So what I'm showing you on this slide are 2 different forms of variability that is normally observed in this kind of technology. You have cycle to cycle effects, meaning if you take a single device, you keep operating it again and again, you'll see that every time it behaves in a different way, not identical to the previous run. And then there is the type of variability which is device to device, meaning if you take 1,000 devices, a large array, you operate the first device, you operate your nth device, their properties will not be identical. Now, in any typical digital application, in any deterministic application, your entire energy and effort would be spent on controlling the yield, on controlling the performance here. These distributions would not be seen as good, these wide resistance state distributions or distribution in the IV, or even absolute switching failure. So this is a typical switching curve, set, reset, different memory states, also known as the endurance curve. And you can see that here, the absence of these dots actually denote that the device remains stuck in this state and it did not go back to the state where it was supposed to go. So from the viewpoint of any typical digital application, this is an absolute failure. So this is unacceptable, and you need circuits like ECC or program and verify and reprogram circuitry to compensate for all of this. So this is an absolute no-go for your typical digital application. So if someone comes and tells you that you have a pool of applications where you can use such noisy devices, where you can use such non-ideal or bad devices, or devices which show this kind of uncontrolled behavior, it's a boon. It's a huge advantage. So and then it just becomes very interesting to see that how very scaled technology, new materials which are not very reliable, can still serve some useful purpose. So this is a very central theme to most of our work, where we have illustrated several different variants both at the synaptic and the neuronal level across different technologies, that how you can manifest these non-idealities into something meaningful. Okay, so if you try to put all these things together on a single map, so there are different possibilities. You can start with a binary memory technology, binary switching technology, you can manifest some intrinsic stochasticity. Intrinsic meaning its internal physics, which will purely be a device or material based manifestation. And how you extract this, one way to extract this is to intentionally use weak programming conditions. So every device will have a certain programming thresholds or programming conditions. If you play below those thresholds, or if you intentionally use conditions which are close to threshold but don't really cross the threshold, you start seeing unexpected behavior in the devices, right? So so that is a very energy efficient way to play with this kind of technology using weak programming conditions. At the same time, if you're not comfortable working with weak conditions and you want some sort of control, better control in your hardware, then you can use binary deterministic devices and go for extrinsic stochasticity circuits. You can add external noise circuits or external RNG circuits, PRNG circuits to your system. So there are different tracks. At the end, what you're exploiting is the same thing. That is some sort of you're trying to create some sort of noise at the synaptic or the neuronal level. Okay. So quickly, I'll just show you few examples of the neurons. So we devised the stochastic integrate and fire neuron, and this was based on the cycle-to-cycle variation of the CB-RAM devices. And the way how it worked is that it exploited the filament dissolution distributions of the CB-RAM device. That is how it was placed in the circuit. More recently, this is a very recent work that came out in Nature just a few weeks ago. What we have done here is we have used bilayer oxide-based devices and exploited some non-linear volatile as well as non-volatile properties in the conductance evolution of the device to come up with an entirely new type of LIF neuron, or more accurately, it's an adoptive LIF because the threshold increases with each firing event, and the conventional ALIF or the adoptive LIF neuron that you would see in literature has a decay profile which has a single time constant. So here what we saw is that the devices had properties where when you're trying to program the device, you could end up with two different time scales. You can end up with a conductance change which was extremely fast and a conductance change which was extremely slow. So we asked ourselves, can we utilize that property of having two different temporal conductance change dynamics in the same device for something useful? And that's where we came up with this DEXAT, or the double exponential adoptive threshold neuron. So the double exponential here is basically two different operational time scales in the decay profile of the ALIF neuron. And what we found is that if you have this kind of multi-time scale decay in your activation functions or in your neurons, that helps you in many ways when you're talking about recurrent spiking neural nets, or when you're working with data sets that are more complex on the temporal axis, that have more complex attributes on the temporal axis. So we were able to show some good learning results on some toy data sets such as SMNIST, Google speech commands, and so on. So now so you have the neurons, you have the synapses, and what one can do is build fully functional unsupervised SNNs. So there, as I already pointed out, with different devices, we have demonstrated through simulations and small realizations that how one can go about the processing of the data from cochlea or retina. So this is purely unsupervised. On the stochastic or the variability induced properties, there are things like ELM or extreme learning machines, and then they can be used for applications such as image segmentation and so on. So how much time I have? I think I have like 5 minutes, or
yeah, that should be fine.
Okay, yeah. So then what I'd like to touch upon is a more recent use case which is related to limb or logic in memory, and we the variant that we came up with, we call it SLIM, or simultaneous logic in memory. So most limb approaches that you would come across while the memory devices are being used to manifest some sort of logic, but the moment you execute logic on them, what you would realize is that there is some loss of whatever previous memory state they were holding prior to the execution of the logic operation, or when you're using it for the logic application, you're totally using it for logic application and you're not using it for memory anymore. So what we felt is that, if you have a memory array sitting next to your controller or your CPU, if you do limb, there is no doubt that head-to-head, the performance that transistors or that pure CMOS logic gives you, there is no way you can beat that, with the devices that we have today when it comes to logic. So the main benefit that limb logic in memory or in memory computing would offer, if you are really able to do some computation in parallel and do that while still not losing what you're storing in the memory. So it would be a great advantage if you somehow manage to retain whatever was there in the memory, and you sort of have a flexibility that you can go back to that block of hardware and start using it as memory again when you wanted to use it as memory, and when you want to use it for some side logic activities. So that is why we call it SLIM. We came up with an approach on these bilayer devices which is a non-destructive limb approach. Hence, we introduced the term simultaneous over here. So this has merit that it gives you the flexibility in choosing when the same block you want to use as typical memory or as logic while retaining both. So quickly, I'll just summarize some more, let's say plug and play applications or more digital applications. What we have worked on is replacing the SRAM or the volatile SRAM using the non-volatile STT or the non-volatile MRAM inside accelerator designs. And as expected, we have seen significant gains when you start replacing the volatile pieces of the memory with non-volatile, because one straightforward advantage that you get is that there are many instances where you can now completely power down your system. So there are applications. We came up with an architecture which is known as NVIDIA or non-volatile inference accelerator, and there are applications which are very asynchronous or asymmetric in nature. So they're always on. A large network of environment sensors or IoT sensor nodes, or doing activity with a variable sensor on smart wearable device. There can be activities which are not uniform, may come to action only for a few minutes in a day, and then may not come into action for the next 3 days at a stretch. But what do you do if you're working with a battery backed system? Do you always keep it on? Do you always keep waiting for? Do you always keep processing it with a uniform sampling? If you have a SRAM driven system, or a system which is extremely volatile or massively uses volatile blocks of memory, you don't have the liberty to completely turning it off. So for those kind of use cases, we were able to show significant gains by realizing the new NVM even in a very digital way, replacing the SRAM with some state-of-the-art technology. So the applications can be like environment monitoring, building monitoring, and so on, which require a very long turnaround time, expecting a very low stimuli or very non-uniform or asymmetric form of stimuli. So I think last thing that I want to just touch upon is that as we move towards 3D integration and as more complex forms of packaging, the sensing, logic, and memory dies are being clubbed together. They're coming together. So again, the typical use case that if you put a sensor array with the memory array very close to it, primary use case is just for storage. But we're trying to answer this question: what more can you do if that memory array, either on the same die or extremely close to it, can start participating along with the sensor itself? Can it use utilizing its properties, its nonlinear or its analog properties or whatever? Can you somehow help the sensing mechanism in additional ways rather than just storing things over there? So we have shown some of the early works on how you can exploit some of these resistive memory devices by clubbing them with image sensors, either by enhancing the performance of the image sensors or just doing some very close to sensor analog compute. So I think I'd like to conclude with that, and to summarize, as emerging NVM has a very significant role for ML, AI sensing as well as security applications. The building blocks that I touched upon in the interest of time here were neurons and synapses. I touched upon some key aspects that you need to keep in mind while designing them with the NVM devices. And again, even at the learning rule level, the point is that you don't have to be extremely biomimetic. You can take some bio inspiration and then start tweaking these learning rules which are more hardware friendly, and then compensate for the changes at some layer in the network to achieve the similar learning or inference results. Now, the very interesting point or takeaway being is that it's no longer a game of just deterministic properties. One can really use probabilistic or noisy properties of these devices as well. And the overall playground that you have with these devices is it cuts across different layers. There are some things that you can do in the device level, circuit level, architecture, and so on. So that is what I'd like to say at the end. So that's also what makes it way more interesting than many other topics to pursue. So again, all of this is really not possible without the brilliant students, research staff that we have working day and night. So I'd like to thank them. Obviously, I'd like to thank all the funding agencies, sponsors, and once again, thanks to the organizers of ICTIC. Yeah, I'll be happy to take any questions that you have.
Yeah, thank you for your very insightful talk. I think we have some questions lined up, and some questions are, I think, straightforward. We'll start with that. Are memristors and RRAM same? That's the first question.
Yeah. So I mean, personally, I don't like the term memristor, but yeah, in a way, you can think of memristor of a more theoretical equation framework of a certain memory resistance or memristive characteristic. But yeah, in the community, people do use the two terms interchangeably. So you will find many people calling RRAM as memristor or memristor as RRAM, but the origin of the term for memristor is more from the theoretical framework, or the really valuable insight that came even long ago when these devices, how easily they exist today, were not existing. So from the theoretical point of view, they are that is really an important framework, a really valuable framework. Yeah, it's in the community. It's being used in an informal way to refer to both things, but the term originally is more for the framework of equations.
Okay, so we have another one. It's an interesting question. How is the in-memory computing faring for non-AI applications?
So I think that is a very interesting question, and at least from the little bit that I understand, the analog in-memory computing, where you're trying to do vector matrix multiplications, or you're trying to get a result from the entire crossbar, in a single shot or in fewer cycles, where you're exploiting the KCL or the current integration. So those cases are a very good natural fit to matrix multiplications, again, and the primary application of our day and age, which is picking up steam these days, again, your convolutions or the matrix multiplications in your AI application. So that is a direct fit. So that is a very natural fit. Now, the other type of in-memory computing, where the it's not really an analog matrix multiply, but it's the realization of some digital gate. Maybe building a NAND gate or a NOR gate by taking a memory device with a few transistors around it is something different. It may not directly be the most efficient thing for your AI matrix multiplications, but it may have some use cases even for non-AI applications where you are frequently invoking the gates. So does that answer the point to some extent?
Yeah, I think yeah. So there are more questions coming in, so I'll just try to summarize. So one question is, do we have any existing software libraries to test neuromorphic architectures?
Do we have any existing software libraries to test neuromorphic architectures? Yeah, I think there are a lot of resources for SNNs, and those resources are growing every day. But I think you will find them more in the typical software SNN community. There are things like BindsNet and many other frameworks. So yes, there are a lot of tools, and they're growing every day.
So another question is like, how is a simple slim bit cell realized, and can you make like all sort of logic functions with that?
Yeah, so the second part is more easier to answer now. So we go for the fundamental gates, the universal gates, the NAND and NOR, and thus building from that, you can realize any other logic. The first part would really require a talk of equivalent duration to really explain. But over there also we have two flavors of the slim bit cell. We have the 2T 1R slim bit cell and the 1T 1R slim bit cell. And depending on how you program or load the operands or the the exact operation, you can have different combinations. Either you play with the gate of the select transistor or with the anode of the device. So yeah, so it is a more involved thing to answer.
Yeah. And another question, like I think this is to do with that sensor and switching off the sensor when there is no event. So the question is like, when you do that, will it result in data loss and as you need like some period to repower your system?
So that is the whole point, right? With the volatile memory blocks, yes, it would directly lead to loss of information, because the moment you power them down completely, you lose whatever was there, and then you have to fetch it again from some external memory, which is more dissipation. But the fact that is exactly the fact that we illustrated gives you big gains. That if you have NVM sitting in place of the volatile memory SRAM blocks, then you can store there safely, and then you can shut down everything and wake it up only when you need to.
Yeah. And another one is more at a device level, like Aidan is asking about like retention of PCM devices. What is the kind of retention for PCM devices? And maybe we can extend it and also draw a comparison with OXRAM as well.
Yeah. So yeah, I think PCM devices have been shown to have good retention. Also, industry grade retention also has been demonstrated on PCM devices. Then again, depends on the exact materials you use. GST, GT, more stoichiometries, more modifications to the layers. But yes, if the question is that, is there evidence for industry grade retention for PCM? Yes, there is. Though, as you know, PCM devices suffer from the drift issue, and then again there are mechanisms to correct that drift and get around with it. So we don't see a real problem in the retention with PCM devices, at least, let's say. And I think the second part was on OXRAM, right? OXRAM. Yeah. So even OXRAM devices, at least the filamentary OXRAM devices, have been shown to have good retention characteristics, industry grade retention characteristics, and the interfacial or bilayer OXRAM devices, they do suffer from a retention problem. They do have a sort of leaky behavior as observed in many stacks, and in fact that is what brings along that additional analog properties or additional time scales into the picture, which one can use. So yeah.
Okay. I think there is one last question, and we'll stop with that. Is in-memory computation useful for DSP application?
So I think we need to be more precise exactly which DSP application. Any signal that is being processed in a digital system is a DSP application.
I think probably the question is coming from the fact that there was like an image processing application, so probably that's.
Yeah. So again, if we take at the basic building block of in-memory that we are using, right? So if you're breaking down your operations into matrix multiplications, then the analog in-memory would be, again, it would be helpful. If you're breaking down your compute on a very gate-centric digital realization, edge detectors or any other sort of convolution. So then again, you will benefit from in-memory.
So I guess that completes it. I think, thank you, Manan, for joining, and spending the time and giving a very interesting set of thoughts on various things that you did.
Thank you so much, and thanks to your entire organization team for having me.
So